Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to guide you through this one, so grab your safety helmets because today we're adopting the mindset of a consulting civil engineer for an exclusive on-site masterclass. We are going to explore the complete guide to modern septic engineering and construction, drawing directly from the expert insights of engineer Abukarta Bavakadi. Whether you're planning a build or, just kind of fascinated by the hidden mechanics of the world around us, you are in exactly the right place.
When we build or buy our dream homes, we almost always focus our attention on the beautiful stuff above ground, right? The fresh paint, the massive windows, the landscaping. But I want to challenge that focus for just a second. What is the absolutely most important system hiding just under your feet? It's the unseen, critical health infrastructure that protects your family and the environment every single day. The true hidden hero of your home is the septic tank. So here is our site visit blueprint for today. We'll be hitting 5 key areas: the hidden house hero, building the foundation, the micro-world process, pitfalls and upkeep, and we'll wrap it up with quality and trust. Let's get right into it. All right, section 1, the hidden house hero, anatomy of a septic tank. Okay, let's dive into this. Imagine we suddenly have X-ray vision of your backyard, and we can see straight through the soil to the structural chambers below. When wastewater flows from the house through the inlet pipe into that very first chamber, physics just takes over immediately. The first thing that forms is the scum layer. Because oils, greases, and lighter waste materials are less dense than water, they literally float right to the top. It basically acts as this organic seal on the surface of the water in the primary chamber. Now, if we look beneath that surface, past the clear water zone in the middle, we find the sludge layer. This is the heavy, solid waste that settles completely out of the wastewater and sinks down to the very bottom. This physical separation, scum at the top, clear water in the middle, and sludge at the bottom, is absolutely crucial. That bottom sludge layer is essentially the engine room, where the heavy decomposition takes place. And then, once that water is clarified in the main chambers, it has to go somewhere, right? It flows out through the outlet pipe to its final destination, the soak pit. This is a highly engineered underground chamber filled with specifically graded gravel and sand. As the clarified water enters this pit, it slowly and safely infiltrates the surrounding soil. It acts like a massive natural filter, which is vital for environmental protection, ensuring our groundwater remains totally uncontaminated. Section 2 already, building the foundation, proper construction and design. So, we know the anatomy, but how do we actually build this hidden fortress? Constructing one of these is a really rigorous, highly sequential process. First, it starts with precise site marking and excavation. Then the builders lay down a plain cement concrete, or PCC layer, followed by heavy reinforcement to cast an RCC base slab. That's the unbreakable floor. Next up, you build the structural walls, including the internal partition. Apply plaster, and, this is key, waterproof the entire interior. Finally, the pipes get fixed in place, a heavy cover slab with an inspection hatch is dropped on top, and the whole thing is carefully backfilled. Every single step demands total precision. Now, what's really interesting about this is how personalized these engineering variables are. You absolutely cannot just buy a one-size-fits-all tank off a shelf. When you break down the design elements, capacity is mathematically tied directly to the number of family members living in the house. The dimensions rely on a strict minimum liquid depths and specific chamber sizes to allow enough time for the waste to settle. Placement is heavily regulated too. It has to be a very safe, calculated distance from any groundwater well to prevent contamination. And the infrastructure itself requires exactly the right pipe slope for gravity flow, plus essential ventilation to handle gas buildup. Moving on to Section 3, the micro-world process, the internal working. We've seen the macro-level concrete dimensions, but what makes the system actually work? Well, deep inside that sludge layer we talked about earlier, there is literally a massive invisible workforce, anaerobic bacteria. Because they thrive in an oxygen-free environment, their entire job is just to continuously eat and digest the organic solid waste. But here is the critical part to remember for later. As a byproduct of all this decomposition, they produce significant amounts of gas, specifically methane and carbon dioxide. This bacteria is the beating heart of the system, its biology doing all the heavy lifting for us. Let's trace how this builds into the complete journey of a single drop of wastewater. It's a brilliantly balanced chain reaction. Step 1, the waste enters, solids settle, and the sludge layer forms. Step 2, the oils float up to form that scum seal. Step 3, our invisible workforce of anaerobic bacteria goes to town digesting the waste in the sludge. And finally, step 4, because the solids are constantly being broken down, the newly clarified water in the middle zone gets pushed through the outlet pipe and flows to the soak pit, like clockwork. All right, section 4, pitfalls and upkeep, maintenance, mistakes, and safety. Now that beautifully balanced cycle, it's fragile if it isn't respected. And this brilliantly illustrates the stark difference between failure and success in civil engineering. Think about the classic amateur mistakes: missing vent pipes that cause explosive gas pressure, the wrong pipe slope causing awful blockages, leaking walls letting raw sewage seep into the yard, or placing the tank dangerously close to a drinking well. It's a nightmare. Compare that to the professional standard: properly vented to release methane, precisely sloped pipes, completely waterproof chambers, and a safe distance from water sources. The professional way guarantees health, the amateur way basically guarantees disaster. So listen, fixing or maintaining these systems, it is definitely not a weekend DIY project. Those gases produced by the bacterial decomposition, methane and hydrogen sulfide, are not just foul-smelling. They are highly toxic, flammable, and honestly, potentially lethal in confined spaces. Professionals use incredibly strict safety protocols. They wear full personal protective equipment, they use calibrated gas detectors, and they absolutely never enter a septic tank without the right safety gear. Routine maintenance, like desludging or keeping harsh chemicals out of your drains, is fine for homeowners to manage, but physical entry, that is strictly for equipped professionals.
Finally, Section 5, Quality and Trust, the final sign-off.
As we wrap up our site visit today, it really all comes down to the expertise of the people designing and building these systems. A house is only as good as the foundational engineering that supports it. And this level of rigor is exactly what professionals like consulting civil engineer Abakar Bavakati bring to a project. His firm, Bavakati Constructions, over in Hunagund, operates on a very simple, clear philosophy: building trust, delivering quality. Because relying on qualified experts ensures that every single step, from that PCC-based slab all the way to the anaerobic biology, functions safely for decades. Which leaves us with a final thought to ponder. The next time you look at a beautifully constructed home, just take a moment to look at the ground. If the foundation is stunning up above, ask yourself, is its unseen hero truly engineered for safety down below? Thank you so much for joining me on this explainer. I really hope you leave with a newfound appreciation for the incredible engineering hiding right under our feet. Keep learning and stay curious.